The music today is Bruno Mars' Count on Me. Okay, this is a song about friendship, about interpersonal bonding. Right, so today we will talk about composite beams, which are formed by bonding different materials together. Okay, it's a material bonding instead of interpersonal bonding. Okay, our objectives will include explain assumptions in composite beam. We will understand the bonding between different materials, how to simplify it, and how to convert different materials into a monomaterial. Okay, we will just basically transform the sections into monomaterial sections so that we can leverage the knowledge we have learned in previous sections to calculate the Y bar and I, and then solve the problem, calculate the bending stresses in composite beams. Okay, before we talk about section transformation, then we will review how to calculate the bending stresses in beams. Okay, the equations are very simple, and we have learned that the bending stress, its nature is actually a kind of a normal stress. Right, so the normal stress in a bended beam equals m times y over I. Right, m is the moment, I is the moment of inertia, right, and the y is the distance from the neutral axis. Right, so at a specific plane, the maximum bending stress equals this m is a constant, I is a constant, so equals mc over I. So here the c equals y max. Right, this is the maximum distance from the neutral axis. Normally this is just the top or the bottom surfaces. Right, we have given several examples to talk about how to use these equations to calculate the bending stress. What I'm showing here is from our after class exercise 13. Right, it's the example 8 in that after class exercise. Okay, let's look at this example. Okay, so here we have a cantilever beam, and we're requested to calculate the maximum bending stresses in the cantilevers with cross sections. Case 1 is just B times H. Okay, case 2 is just 2 sections B times H put together, stacked together, but without interfacial bonding. They're just 2 parallel beams carrying a load P. And in the third case, it just get these 2 sections, the same material, perfectly bonded together, or you will get a cross section B times 2H. Okay, so in these 3 different cases, let's calculate the maximum bending stress. Okay, in case 1, okay, this is really simple. I think we just calculate the stress from M1C1 times I1. Right? So since we're calculating the maximum bending stress, we just need to find the maximum bending moment first. Where is it? It's just at this end, right? We have done many exercises, so you should be able to identify the maximum M very easily, right? In this case, maximum bending moment just equals PL, right? So here in this case, the M1 equals PL, and what is C1? C1, just since the neutral axis is just in the middle, right? So the C1, just the maximum distance from the neutral axis, that would be half H, right? And the I1, just B H cube over 12, right? So we can easily calculate the maximum bending stress in case 1 that would be PL times H over 2 over BH cube over 12. Right, so that would be 6PL over BH squared. Okay, then in case 2, the equation will be the same. It's sigma 2 equals M2 C2 over I2. Okay, so in this case, since we have said these two sections are not bounded at the interface, so they are just two parallel beam sections carrying the P together. So each of them will carry half P, right? So what is the M max? So the M max in each one of them will be PL over 2. Right? Of course, here you have the same value. Right? You have two bending moments carried by each of them, and each of them just equals PL over 2. Okay, so in each of them, what is the C value? Since you have two parallel beam sections, each of them will have a neutral axis, and the maximum distance from the neutral axis will still be half h, right? So the M2 will be PL over 2. And the C2 is still h over 2. And the I2 of each of them will be the same, right? Equals I1 will be BH cubed over 12. So the maximum bending stress in case 2 will be PL over 2 times H over 2 over BH cubed over 12. This will be just a half of the max stress in case 1. Right, it's half of it. This will be 3 times PL over BH squared. And let's look at number 3, the case number 3. Okay, since just two beam sections from case 2 are perfectly bonded to each other to get a larger cross section, B times 2H. Right, so the basic equation will be the same, right, just M3 C3 over I3. Right, so what is the M3? M3 this time, since it have been perfectly bonded to each other, so we can consider that this is one piece, right? It's a one-piece material, right? Monomaterial cross section. Okay, so at this end, the M max will be what? PL, right? M3 is PL, and C3 will be H, right? Since your head had been 2H, so half of it will be H. So the I3 will be B times 2H cubed over 12. It will be 2BH cubed over 3. So the maximum bending stress in case 3 will be PL times H over 2/3 BH cubed. So this will be 3PL over 2 BH squared. Okay, so you can see that in which case you have the maximum stress, in which case you have the smallest stress. Right, the smallest stress is here. Okay, so in this case 3, we have these two beam sections bonded together. Then how about, and these two pieces are the same material, right? So then how about if these two materials are not the same? Okay, if one piece is steel, the other piece is wood or aluminum, then how will we deal with it? So this is called composite beam. Okay, this will be the topic today, and we will talk about how to transform this composite beams consists of different materials into a monomaterial cross section.